have a small bead here. If I release the bead, maybe give it a little nudge, it gets pulled into a point and tends to stop right about here. If I release it from here, well, it kind of follows a little bit of a complex path, but it ends up at the same spot. If I release it from here, or here, or here, or here, it tends to get pulled into the same spot. And the closer it is, the more quickly it changes its velocity. Further away it is, the less quickly. If it's too far away, it appears to be reacting to something besides whatever it is here. And it turns out that this is a metallic bead and there's just a magnet under here. The field is a little less uniform than what I'm going to draw, but I'm going to indicate the effect of this field by drawing a series of vectors from a set of points lying on a circle around this central point, indicating that from any one of these points we expect the force field to pull this bead toward that point. We can test it, release the bead here, release the bead here, release the bead here, and so forth. Now actually, if we release it here, it appears that the bead's going to follow kind of a circular or spiraling path into the point. So the sketch that I've drawn here isn't perfect, but it'll serve to represent the idea of a certain type of a force field. And I'll note that this larger ball is also subject to the same field. Okay, except something weird's going on here. But let's pretend that the field is as we've sketched it. Another aspect of the field is that it gets weaker as we move away from the point. So if we want to sketch the field at a series of points somewhat further away, the field appears to be weaker. It's going to be represented by shorter vectors. The length of the vector indicating the strength of the field. Now if I release the ball out here, well, looks like it tends to pretty much move toward this point, maybe out slightly, and this will actually be a very short vector, much shorter than this one. So when we get out past this range, I'm just going to indicate the direction of the field. From here, that doesn't look like it makes it in there. It looks like maybe the field's like so. Out here, not much. Field's pretty much appears to be zero out here. Here, not much. Okay. Now, this is just one example of a force field. There are many other examples of force fields, and they don't all have the characteristic of this one that they point to some central location. But it should be clear that if I draw a circle around this point, or any approximation to a circle, in fact, any closed simple loop or curve around this point, that the field, according to our depiction here, appears to be flowing inward at every point, so that there's a net inward flow in any simple curve approaching this point, or enclosing this point. That's one important property. So there's a net inward flow. And if we had a bunch of small magnetic particles scattered about this point, they would tend to flow inward. Now, the question's a little more complicated. If I want to consider a region that doesn't enclose this point, it's less clear what happens. So if I take a region, let's say here, take a curve, okay? Is the net flow inward? Is it outward? Could it possibly be zero? If we look at this region, and let's draw a slightly larger depiction, in other words, let's kind of move this region over here out of the picture and depict it here. The field is smaller on this edge of the boundary, so we have a kind of a small inflow here, and the flow appears to be greater on this side. Getting smaller as we move further from the center. So it would appear that there's still perhaps a net inflow from this field. And I said that wrong. There'd be a net outflow because the outflow vectors are bigger than the inflow vectors. So, question here looks from this picture like a net outflow from this surface, or through this surface, rather through this curve. We could generalize this to a surface, of course. We could have a spherical distribution that always pulls things in toward the center. Now, we're talking about a flow here. It's kind of a flow of the field. It's not necessarily a flow of actual material, although, again, if we had magnetic material scattered around, it would tend to flow toward this central point. If we had a bunch of material scattered around here, of course, it would eventually accumulate and fill this region. So we might imagine that there's some mechanism here for removing the material once it gets into the center. In which case, if we maintain a supply of magnetic material out here, we'll have a continuous net inflow of material. But since the material tends to accumulate, again, we would need some mechanism of removing it from this point. Now suppose that in 2 or 3 dimensions, these arrows represent the flow of a fluid like water. If it's a water flow, then it can't accumulate at a point, since water is essentially pretty much incompressible. At least at ordinary pressures. And ordinary pressures in this context would include the pressure at the bottom of the deepest part of the ocean, where in our everyday experience the pressures are enormous. Water is very difficult to compress, so in ordinary circumstances we're going to consider water to be incompressible. And if that's the case, water can't accumulate at the center, just like magnetic materials couldn't accumulate here unless there's some way of pulling them away. So we could imagine maybe a thin tube here that's pulling water out of a reservoir when we do have water maybe being replenished in the reservoir. so that we could have a net flow of water, but only if there's a way for the water to be taken away. And I'll also say that if it's a water flow from the same characteristic being incompressible, water can't expand to fill a volume. Of course, it can expand a little bit if you change the temperature, but we're going to assume we have an even temperature. So we'll say nor can water have a net outflow through any closed region. Now, I haven't really defined the term closed region, but intuitively that simply means if this was a region of space, for example, and we had water flowing in 3 dimensions, if this is a nice simple closed region like an ellipse or a circle or a box or something, we can't have a net flow of water in or out. And that holds, unless there's a source within the region. Now, by source, I mean either a way of removing or introducing water into the region. For example, we thought of the example if there's a tube pulling water out of the region. Well, we could reverse the flow. We could pump water through the tube and it would flow into the region, so we could have a water flow into our region, resulting in a net flow across the boundary that's away from that source. Similarly, in a region like so, if there is a source, either a way of removing water from or introducing water into the region, then we could have a net outflow or even a net inflow. So we started out with the idea of a force field, and now we're talking about an idea of a flow field. Should be clear that both kinds of field could be represented by arrows, and any set of arrows could represent, at least theoretically, a force field and or a flow field. Also, that across different regions we could have net inflow, we could have net outflow, we could have net zero flow. Where the word flow applies literally to a fluid flow, applies figuratively to a force field.